We know how atoms work. They're not a mystery to us. And they work in such a way that when you die, there is no way for the information that was you to persist after death. There's no way for that stuff, that knowledge, that set of beliefs and feelings that made you you to leave your body, because it is stuck there with the atoms that is decaying in your tomb or being cremated or whatever your favorite way to be after death is. So I want to emphasize, I want to make a little bit of an argument, a very, very, very little bit of an argument for the statement made in red that we know how atoms work. The point is that the laws of physics, we don't know all the laws of physics by any stretch of the imagination, but those laws of physics that are relevant to the atoms in your body, we know all of the laws of physics that far. There's no room for new laws of physics that would affect how the atoms in your brain actually work. That's a very subtle statement. So I could, I think that Dan mentioned I had 3 hours to give this talk, but I would get tired if that happened. So I would give you the whole explanation for the laws of physics, how they came to be, why we're confident, but instead I will just intimidate you in submission by showing you an equation. So in this one equation are summarized all of the laws of physics necessary to understand the atoms in your brain at the energy, mass, and length scales relevant to your everyday lives. We have quantum mechanics, we have space-time, we have gravity, we have the other forces, electromagnetism and the nuclear forces, we have the matter, the electrons and the quarks of which you are made, and we have, of course, the Higgs boson we discovered. Higgs boson fans also, 2 years ago. The point is, again, there's plenty of room in the laws of physics for other stuff. We don't know how black holes work. There's plenty of things we don't understand. I'm not saying that physics is done. I'm a physicist. I know it's not done. I'm not going to retire soon. But we know enough to say that if there are any other forces, particles, fields, phenomena, they can't affect the atoms in your brain, because either they're so weak that they would have no effect on what the atoms are doing, or we would have found them in experiments. Those are the only two options. So no one ever understands me when I say this, so I'm going to say the same thing over again. Here are the caveats to this statement. I'm not saying we understand all of physics. I'm not saying that there's room for no new discoveries in the non-everyday world. I'm not even saying we know how the fundamental laws come together to make complicated macroscopic things like frogs and ecosystems and spiral galaxies. There's enormous amounts of work to be done in understanding how science works. But we have an underlying framework, which we call quantum field theory, as Dan mentioned. And quantum field theory is either true or false. All the evidence says that it's true, and if it is true, then there is no room for new physics that can in any way affect what goes on in the atoms in your brain. We understand what they do. There is therefore no room for the information that is you to persist after you die. And yet, even Alexander, bow tie and all, sells a lot more books than I do. He's #1 on the New York Times bestseller list. There's a few books back there. We can change that tonight, folks. Don't you agree? Why is it? What are we to do with people who say that they have evidence that there is life after death? I like to put it in terms of two options, and either one you are allowed to choose, but you should know what options you're choosing. Option one is that some ill-defined metaphysical substance not subject to the known laws of physics interacts with the atoms of our brains in ways that have thus far eluded every controlled experiment ever performed in the history of science. Or people hallucinate when they're nearly dead. I leave it to the court to decide, but not the Supreme Court, because as we've heard, they would get the wrong decision. But going beyond claims of people who have actually visited heaven and come back to sell books about it, because that's the mission that they were given, we can be scientific about this. We can ask, okay, given that we're made of atoms and we understand what the atoms are doing, what is life? What is this complex, non-fundamental phenomenon that arises out of the motions and interactions of the fundamental particles of which we are made? And this guy, Erwin Schrödinger, famous Austrian physicist, he was one of the very few Well, there are many, many famous physicists who fled Austria and Germany just before World War II. Most of them fled either because they were Jewish or their friends were Jewish or they were appalled at Hitler's treatment of the Jews. Schrödinger fled because he was having trouble keeping his mistresses. And he tried to get a job all over the place, and finally in Ireland at Trinity College, they said, sure, well, yeah, no problem. So he moved to Ireland and became a biologist, and he wrote a little book called What is Life? And this book became quite famous because he prefigures a lot of what we soon thereafter discovered in terms of DNA and the genetic code, just by the basis of thinking like a physicist. But he also tried to address the question in the title of his book, what is life? When is a piece of matter said to be alive? And it's a wonderful, thought-provoking answer. Basically, he says something is alive when it keeps moving long after it should have stopped. That's what it means. If you have a little chicken, baby chick, grows up to be a chicken, as long as you feed it, it's going to move around. It's going to flap around and raise its wings and so forth, cluck. When it dies, it will stop moving. It will decompose and will return to the ground. And so Schrödinger wants to know, what is going on? What is it that keeps alive things moving and walking around and making noise and raising a fuss? And the answer, as he quite correctly puts it, is my favorite law of physics, the second law of thermodynamics. Second law of thermodynamics is this is not the same chick that was on the cover. Death. What can you do? The second law of thermodynamics is the law that says that the entropy of the universe, or of any closed, isolated bit of the universe, increases as time goes on. Entropy is simply a measure of the disorderliness, the messiness, the chaotic nature of stuff. If you start with an unbroken egg, it is easy to break the egg. That makes it more disorderly and disorganized. It is easy to turn that broken egg into scrambled eggs. Again, more disorganized. It is very, very difficult, and would never happen by itself, to take the scrambled eggs and make it back into the pristine form of an unbroken egg, Humpty Dumpty notwithstanding. So this law is very, very profound, and it captures people's imaginations at a sort of social and personal level as well as a scientific level. It also captures the imagination of creationists, because they say, look, there's a fundamental law of physics. You're telling us one of the famous laws of 19th century science says that things run down, that things become less and less organized over time, that ultimately the universe will reach heat death. And yet, you expect me to believe that all of the marvelous complexity of life and the biosphere and evolution that you guys talk about all just happened here on Earth, starting from some disorderly primordial goo. How is that possible? Now, there's two answers to this. One is the simple and perfectly correct and short answer, which is isolated systems, we said. And the Earth is not an isolated system. There's a little story you can find on the internet. I'm not sure whether it's true or not, but it's a creationist saying, you know, the physicists always say the Earth is not an isolated system, but that can't be right, because if it were, there would be a giant glowing ball of energy in the sky. Yes. That's probably not true. I mean, that's just too good to be true that anyone ever said that. But indeed, the reason why things like this, so I said that's one answer which is completely true. The other answer to the creationists is a more subtle one, which is to say, you know, you're right. It doesn't seem to violate the letter of the law in terms of the second law of thermodynamics for life to arise on Earth, but does it violate the spirit of the law? Why is it that complicated, elaborate, complex organisms arose just through the impersonal working out of the fundamental law of physics if there was no guidance there? If anything, the tendency seems to be towards messy disorder. And so here's the Earth, there's a picture drawn by a famous artist named Roger Penrose. And what you see is that the sun is a hot spot in a cold sky. If the whole sky were the same temperature as the sun, the Earth would get a lot more energy. Energy is good, but the Earth would soon come to be the temperature of the sun and we would all die. If the whole sky were the temperature of the night sky, the Earth would come to be the temperature of the night sky and we would all die. The reason why we are here and life arose on Earth is because the sun is a hot spot in a cold sky, and what happens is we get low entropy energy, orderly energy from the sun that is able to do useful work. We chew our cud and we photosynthesize and we have conventions and we degrade that energy. We raise its entropy and then we send it back to the universe. For every 1 photon of light we get from the sun, we radiate back 20 photons back into the universe, 20 times the energy. 20 times the entropy, 1/20th of the energy per photon. We give exactly as much energy back to the universe as we get. The sun is not useful as a source of energy, it's a source of low entropy energy. And the thing that we do with that low entropy energy is we make life and do what life does. And this is not just here in our biosphere, this is something that is characteristic of the universe as a whole. So let me remind you of the history of the universe. Here's a picture I took of the Big Bang. This is right after the Big Bang, 1 second. And now sometimes you will see the Big Bang, which happened 13.8 billion years ago, portrayed as like a bright dot in a black background, and that is completely wrong. That makes you think that the Big Bang was an event with a location at a place in a pre-existing space-time, which is not right. The Big Bang is the whole universe coming into existence. So this is what it would have looked like if you were there 1 second after the Big Bang. It was hot, it was dense, it was smooth, it was the same everywhere. It was shining with the brightness of, I don't know, some really bright thing, the whole universe. As time goes on, here's a snapshot, and this really is a photograph, 380,000 years after the Big Bang. This is the moment when the universe became transparent. This is an image in the cosmic microwave background, the leftover radiation from the Big Bang. And what you're seeing now is the gradual formation of structure. The universe is growing increasingly lumpy and inhomogeneous. The blue spots are a little bit emptier, the red and yellow spots are a little bit heavier, a little bit more dense. And if you let time go on, gravity increases the contrast knob of the universe, and we get this wonderful, beautiful picture of galaxies and stars and superclusters. And this is the Hubble Ultra Deep Field. This is now about 10 to the 10 years after the Big Bang. One of the iconic and most beautiful images that human beings have ever produced. If you point your telescope at a blank spot of the sky and you open the shutter on your camera, then this is what you will see as long as your camera is hooked up to the Hubble Space Telescope. This is what you will see. We live in a world with hundreds of billions of galaxies, and who knows how many conventions are going on with extraterrestrials fighting to keep church and state separate in their local environment. And very often it ends here. The story you're told of the universe ends here, but this is not the end. The universe will continue to evolve, even after we're not here. Here's a picture of the universe 1 quadrillion years after the Big Bang. That's because ultimately the stars will burn out. About 10 to the 15 years after the Big Bang, the last star will stop shining. We'll have nothing in the universe but cold rocks and black holes. I know. But even that will not be the end, because all those rocks, those planets, those dead stars, those comets will fall into the black holes. And Stephen Hawking in the 1970s taught us that black holes do not last forever. Black holes give off radiation. They will evaporate. They will eventually disappear. That will take 1 Google years, in the good old-fashioned sense of the word Google before the search engine took over. 10 to the 100 years from now, the last black hole will have evaporated and will be nothing left but empty space. And our best current model is that empty space lasts forever, infinity years into the future. So that's the history of the universe. So here's a picture of the history of the universe, and I want you to notice something about this picture. Entropy increases as the universe expands. So on the left, soon after the Big Bang, the fact that the universe was very smooth is actually, in that physical circumstance, a reflection of the fact that it's very orderly. It was so dense and the gravity was so strong that keeping everything smooth is a very, very rare and finely tuned state of affairs. Entropy grows as the universe expands, structure forms, stars shine, people live and die, and eventually you reach empty space, which turns out, if you go through the math, to be a very high entropy state. But complexity, the organization of the stuff that is going on, is a completely different thing than entropy. On the left, in the beginning, the universe was a very simple place. It was just hot, dense, and smooth. At the end, a Google years from now, the universe will be a simple place once again. It will be empty space. It is in between, when the entropy is increasing from low to high, that the universe becomes complex, that it forms planets and stars and galaxies and living organisms. And that behavior is not an accident. That is a universal kind of thing that complexity does. Entropy just goes up, but complexity first goes up and then fades away once you approach the final state, which we call thermal equilibrium. So the right answer to the creationists is that it's not only is it allowed by the second law of thermodynamics that complex structures like living beings arose here on Earth, but the reason why complex structures like living beings arose here on Earth is because of the second law of thermodynamics. We are parasitic upon the increase of entropy of the universe. We are little surfers riding a wave of entropy until we eventually scuttle up on shore and it will just be empty space forever. And again, the universe is not special. You can see this in a cup of coffee. Or, since I took this picture, this is actually coffee liqueur and cream liqueur because they don't mix as well. So it's a better picture-taking device. If you take a cup of coffee with the cream and the coffee separate, that's low entropy, highly organized, but also very simple. If you mix them together, it is high entropy. Everything's mixed together, but also very simple. It's in between. When you see the tendrils of the cream reaching into the coffee and swirling in little complex patterns, that's when you get the complexity of the universe. And these little swirls, these little ephemeral bits of complexity that are caught in between the simple beginning and the simple end, that is us. That is what we are. We are these temporary eruptions of structure and organization as the universe goes from simplicity to simplicity. So, a couple of years ago, I got lucky enough to be sitting on a plane next to Michael Russell, who is a geochemist at JPL, the Jet Propulsion Laboratory, and he saw some paper I was reading and said, "Oh, the meaning of life. I know that one, that's easy. It's to hydrogenate carbon dioxide." Because as a geochemist, Michael knows that the early Earth's atmosphere was dominated by carbon dioxide, and it turns out that from a chemist's point of view, that is a very low entropy thing to be. There's a much higher entropy thing to be, a place the Earth's atmosphere wants to go to, which is methane. But it can't get there. There's no simple chemical reaction that takes you from carbon dioxide to methane. What there is a complicated system, a pathway of many complex chemical reactions that will take you there. So as the early atmosphere and the early oceans sloshed about, occasionally they would fluctuate into existence just the right thing to do all of the chemical reactions in the right place, increasing the entropy of the atmosphere, and that caught on and became the first living being. That's what life is. And that insight is crucial, I would say, not only to the scientific definition of life, but to our actual lives. This is the thing that in the audience, when I was debating Eben Alexander and Raymond Moody, that the audience who were not on our side, Steve Novella's side and mine, the thing they didn't get the most was, but when you die, where do you go? Isn't energy conserved? Don't you have energy in you? Doesn't it go somewhere? And the answer is that life is not an energy, a force, a spirit, a substance. It is a process. It is a chemical reaction. And the end of a life is putting out a candle. When you put out a candle, the energy doesn't go anywhere. The reaction stops. When you die, you don't go anywhere. Your atoms are still there, but you stop happening. That is what it means to die, and it will happen to you, as you can find out by watching HBO on Sunday nights in the spring. If you wait long enough, we will all reach equilibrium. You know, roughly speaking, it's very, very possible, by the way, that medical science here on Earth will extend our lives by an enormous amount. It's not at all in violation of the laws of physics for human beings to live thousands or tens of thousands of years. But we're not there yet. We don't have that. We, like other mammals here on Earth, get roughly 1.5 billion heartbeats per lifespan, and then that will be it. We will go away. And this is why the afterlife is a false consolation. This is why this wishful thinking, this hope that life is eternal and will go on forever, is not the right hope to have. Or this is why I like to say that heaven is a bad idea. And just like Anthony Pinn pointed out, this wisdom can be found in poets and songwriters. And by the way, Anthony Pinn's talk, how amazingly good was that? I thought that was just brilliant. Heaven is a bad idea because you reach thermal equilibrium and nothing happens. It's boring. David Byrne knows this. Heaven is a place where nothing ever happens, he will tell you. Leonard Cohen knows this. The place was dead as heaven on a Saturday night. Much rather be spending my Saturday night with the infidels here talking about things than in heaven with the angels. There's a fantastic novel written by Julian Barnes called A History of the World in 10.5 chapters. And the last chapter of his book, Julian Barnes puts forward his idea of heaven in fictional form. And there's always a catch if you're in a novel version of heaven, right? So his hero, who's sort of a working class, blue-collar, British duffer, dies, goes to heaven. He has a guide, and the guide explains, basically, here's how it works. It's heaven. You can have whatever you want. The catch is, you have to figure out what you want. It is up to your imagination and capabilities to ask for things. We're not going to make suggestions. So the guy knew what he wanted. He wanted to play golf, he wanted to have sex, and he wanted to have breakfast for 3 meals a day. So he got that. That's what he got. For hundreds of years, he became very good at it. He had sex with all sorts of women in various different combinations. He became so good at playing golf that he got a hole-in-one in every single shot on every single course in heaven. And then, he got bored, and he asked his guide, and the guide said, well, you have the option, everyone has the option here of dying, of truly ending their lives. And he said, how many people ask for that option? And she says, everybody asks for that option, eventually. Because it's a mistake to think that there is some perfect way to be. This is the lesson of our ephemeral, entropy-driven lives. So it's not just heaven is a bad idea, happiness is a bad idea. Now, don't get me wrong, I like happiness, I try to get it myself, I'm kind of happy. I have the best wife ever, Jennifer Willett is how you pronounce her name. You can buy her books too. What I'm against is fetishizing happiness. If you go to the New York Times bestseller list, if it's not proof of the existence of heaven books, it's happiness books. Not a lot of cosmology books on there yet. The point is that we make a mistake because we think that there is some way to be, some situation we can put ourselves in when we reach perfect happiness and then we'll stay there forever. And then that would be like heaven. But the nature of life itself is movement and change and evolution. There can't be a perfect state of being. And there's science behind this. In psychology, they talk about the hedonic treadmill. They do studies. They study people, they measure their level of happiness before and after some life-changing event. If you win the lottery, you become happy, but a few years after, you're the same level of happiness you had before winning the lottery. If you get in a terrible accident and become paralyzed and paraplegic, you become unhappy, but a few years later, you're the same level of happiness you had before the accident. And you can talk about the chemistry of it, and the dopamine is flooding your brains, and you get used to that. You want more dopamine, and you can't get it. But it's just all based on a fundamental flaw. There's no way to achieve this perfect, everlasting, never-changing happiness, because if it's never changing, that's not that interesting, and it won't make you happy. It's a fundamental contradiction. So what do we have instead? And again, I pull up the wisdom of the poets. Muriel Rukeyser is a poet who has one of my favorite quotes. The universe is made of stories, not of atoms. And Rukeyser is not one of these anti-science poets. She wrote a wonderful biography of Willard Gibbs, who is America's greatest 19th century scientist. And her point is, if you meet someone for the first time, you're on a date or you're in Starbucks or whatever, and they say, tell me about yourself. You don't give them a list of all your atoms. Now, I'm a faculty member at Caltech, so there it would happen. It's considered kind of hot at Caltech if you just list all of your atoms. But most of us choose to be a little bit more coarse-grained, to tell a story about who we are and how we got there. And it's that story that gives meaning and success to our lives. It's not the attainment of any one state of being where we get there and we stop. It's a story with a beginning and a middle, and inevitably, according to the laws of physics, an end. And how well that story is, once you're done telling it, is the measure of success of your life. And I say this, and I don't want to belittle the very, very real sorrow that accompanies death. I don't want to make light of it. I think that, we all have friends, family members, loved ones who have died, and it makes you very sad, and that's not a mistake. It is sad when we lose someone that we care about. It's okay to feel that sorrow, to cry, to have whatever reaction you want to. Knowing that it's inevitable doesn't make the sorrow go away, but maybe it affects how you deal with that sorrow. If I may put forward an inappropriate joke, Robert Schimmel, who is a comedian, he's quoted in a wonderful new book that recently came out by my friend Eric Kaplan called "Does Santa Exist?" It's a philosophical, ontological, epistemological look at the difficult question of Santa Claus. So he relates Schimmel's joke, and Schimmel says, my son got cancer, and it was just the most horrible thing. I really thought, I was so sad, I thought that there really could be nothing worse than hearing that your son has cancer. Then I got cancer. That was the joke right there. He got cancer. I'm a physicist, not a comedian. But it reminds me of these pictures. If you ever are in Paris, you can actually go visit what are called the catacombs of Paris. There are many, many kilometers of tunnels underneath the streets of Paris where they have interred literally millions of human skeletons. Because in the 18th and 19th century, they weren't very good at building graveyards, and when it would rain a lot, the skeletons would sort of float down the streets. So they dug up all the graveyards, and they took out all the bones and the skeletons, and they put them in the catacombs, and you can visit. And what I like about it is, it is a very serious and somber place in some ways, but the attitude is very different in Paris than you would get here in the United States. There's a somber inevitability, but there's also some fun. There's some whimsy there. Whoever was arranging the skulls and so forth would make little hearts. And they have little mottos, they have little quotations up on the wall. So here's a quotation, and if you read it, if you translate it, roughly speaking, "Thus ends everything on earth, spirit, grace, beauty, talent, ephemeral like a flower blown away by the slightest wind." And the attitude is basically, you're laughing now, but you'll be here before too long. The point is that death is serious. It does happen. It's okay to treat it seriously. But the reason why it's serious is because life matters. Because the life we have right now is not a dress rehearsal. It's the only performance we get to give. I'll end with this picture, which is the favorite picture. I always say that if I ever work up the courage, someday I will give an hour-long talk, which consists of me asking the lights to go down in the room, putting up this picture, and standing there silently for an hour as everyone contemplates this picture. The universe can be kind of overwhelming. We are very, very small. We are a very, very tiny part of the universe, but we are a remarkable part. We are just collections of atoms, but we are collections of atoms that have attained the ability to think about ourselves, to reflect about the world that we live in, and to write our own stories. Our lives will not last forever, and that is what makes them matter so much. Thank you. And we do have time for questions. Should I just go ahead? Okay.
Thank you. How can we teach those that hold a religious belief, or rearrange their atoms to say, to teach them what the definition of a scientific fact is?
I don't know. I think that given some time with a good-intentioned, well-meaning religious person, teaching them the definition of a scientific fact is not going to be high on my priority list. I think that if you actually want to know how to reach people, how to change their minds, if the word fact comes to your mind, you've made a big mistake already. And that is a fact. They have done studies. If you have somebody that has a belief that you don't agree with, and you hit them with facts that are incompatible with their beliefs, they will hold their beliefs more strongly. They will not change their minds. If you actually want to change their minds, you know what you should do? You should set a good example. You should lead a good life. You should let them see that people who disagree with them are good people they might want to be, get them thinking about what that would possibly mean.
This is a little embarrassing. It's about your equation. My brother, who knows nothing about it, says there's a typo.
and you're going to tell me where it is. That's it? I don't think that there is a typo. I think you can argue that the second term on the second line should have an absolute value sign around it, but that is dependent on what conventions you use for the covariant derivative. So I don't think there's a typo.
Some say there's no such thing as a stupid question. I'm going to test that proposition right now. Universe roughly 14 billion years old, the Earth roughly 4 billion years old. The years, the time it takes the Earth to go around the sun. What does it mean to talk about a year before there was an Earth, or for that matter, a sun?
Well, what does it mean to talk about a year before there was the Earth? I'm 6 feet 1 inch tall. What does it mean to talk about the idea of 6 feet and 1 inches before I was born? There are ways of measuring things that are independent of the tools with which you use to measure them. When we talk about a year, we mean a certain number of seconds. Pi times 10 to the 8 seconds, or I forget what the number is. Someone knows what the number is. But we measure time passing with things that are much more fundamental than the Earth going around the sun these days. 1,000 years ago, that's what we would have used. These days, we use the vibrational frequencies of atoms and nuclei, for example. So when we say that there's an age of the universe, 13.8 billion years, you should translate that into your head to a certain number of vibrational frequencies of a certain isotope of cesium.
Wow, that actually makes sense.
Sorry?
I say that actually makes sense. Wow.
I tried. Yes.
Yes, first of all, I'd like to say I'm taller than I look. But as far as when you made the comment about the paralysis issue, that really hit home with me, because when I first got paralyzed, yes, I was miserable. But as it turns out, 19 years later, I'm happier than I ever have been.
Good for you.
And a lot of that has to do with coming to grips with being a non-believer, and I thank FFRF for that. But my question is, and it's real brief, when you showed the pictures of the stages of the universe, approximately where did we fit in that grouping?
Yeah, we're in the middle. That's a great question. We are at the stage of the history of the universe. Let me get the one with them all together. It's not an accident that here we are in the moment of the history of the universe when it looks kind of complicated. Now, that's a very broad thing. The universe looked complicated 5 billion years ago. It will continue to look complicated 100 billion years in the future. But on the very, very broad term, if you think about this red curve going up and down, we're near the top. We are living in that part of the universe's history when it's pretty complicated. I'm a cosmologist. I can easily tell you what the universe will look like a quadrillion years from now. I have no idea what the Earth will look like 50 years from now, because technology is moving much faster than I can possibly predict. So whether or not we won't have constructed enormously more complicated things right here on Earth in the very near future is something that is very possible. I just don't know. Yes.
I had 2 quick questions. At the beginning of your talk, you talked about the brain just being a state of atoms, and that we can measure any of the external forces on them. Does that, making a case for there not being life after death, does that also make a case for a lack of free will, and like that there's a inherent destiny in the way atoms interact? And the second question that goes with that is, so is there an ability, would we someday have the ability to take a snapshot of the brain and then save that and let that program run virtually?
Right. So the second one I'll take first. Can we ever possibly take a copy of the brain, a snapshot of it, and run it on a computer? Roughly speaking, the answer is no. I mean, we might sort of technically be able to do it, but the brain has a complexity where if you take a snapshot of it, you're basically building a copy of it. And so that's fine, but you're not going to run it any faster than you run the brain. I mean, you're not going to really learn that much that way. It's certainly possible that we can have things that are like human beings, living beings, but in a virtual or electronic substrate. I mean, I think that's completely okay. I do not think that the way we'll get there is by photocopying brains or states of brains. The other question about free will, I think this is a very subtle question, and the answer is yes and no. The answer depends on your definition of free will, to nobody's surprise. If by free will you mean an ability to somehow override the laws of physics, no, you can't do that. You're made of atoms. If we knew the state of your brain to arbitrary accuracy, and we knew all the laws of physics to arbitrary accuracy, and we had infinite computational power, we could predict what you would do. But the point is that we don't have any of those things. So this is a fact and not a very relevant fact to how we should treat actual people in the actual world. The way that I like to think about free will is as an emergent phenomenon. The right way to think about people, since we don't know where all their atoms are and we can't do the math, is as rational, hopefully rational, agents that have the ability to make choices. Thank you.
Thank you so much. Now we want to